Hi, welcome to another installation of our BQIT lecture series. This will be the fourth video in this series. So today we'll be getting to the basics of quantum circuits. So we're finally getting into the meat of quantum information. So let's start with the concept of a qubit. So a qubit is a combination of the word quantum and bit referring to zeros or one, and quantum referring to, of course, quantum systems. So a qubit can be defined as a two-level quantum system with two energy levels, each level representing each bit. So the lower level is referred to as zero, higher level is referred to as one, and they each correspond to bits zero and one. So analogously, we have what's called the qubit, which is a three-level system, which has three levels, and of course, you have a qubit D-level system, which is D, which is multiple energy levels. So let's compare the two. Well, how is a qubit different than a bit? Well, a bit only has two different states, zero and one, but a qubit has an additional superposition state, which can be represented in general by this formula. So if we have a superposition psi of our two initial energy levels, we can have these in a superposition with amplitudes represented by these trigonometric functions and a relative phase between the two, along with a global phase right here. And the global phase we mostly ignore because it's non-physical. Basically, it just disappears when you calculate the amplitudes of this state psi, so we don't really actually bother to pay it any attention. Now, you can check if this is normalized. It is. If you can follow the algebra here, you can follow that this is indeed normalized. So this is indeed the most general representation of a superposition. So from this framework of qubits, of course, 0 and 1 can be represented by vectors, as mentioned in the first lecture, but there are many different possible basis states, as you can put it, that can represent a single qubit or two-level system. So we tend to refer to the 0 and 1 states as what's called the canonical basis or the Z basis. But you may have different bases such as the plus bases, which is the X basis, and these are formed by simply applying something that's called the Hadamard gate to the first some qubit basis states. And the minus state is formed by one applying the Hadamard gate to the one computational basis states. So you can check that these are indeed orthogonal to each other and normalized. And of course, you can have another basis state called the Y basis state, and these are represented by plus I and minus I. And of course, these are also orthogonal to each other and they are normalized. Now, uh, okay. Yes, as we can confirm over here, this is just algebra. So to quickly go over it, this will be shit. This will be over here. I then multiply this by oops, I did it the other way around. Minus I multiplied by this. Of course, this would be 1 add 1. This is 1. And this is basically the same for the one below. Okay. Now, you may be wondering, why is this called the z basis state and this is the x basis state, this is y basis state? Well, these are basically the eigenstates of the Pauli X, Z, and Y gates, respectively, which is why they have that name. And I think, yeah, we will go into detail about what Pauli gates are later on. So the next topic is what's called the Bloch sphere, which provides basically a quite convenient way of visualizing uh, single qubit states on superposition. So, of course, you may have realized by now, the more observational of you, the astute of you, may realize that the reason I've chose to go with this representation is because of the Bloch sphere notation over here. So the theta in here actually refers to this angle over here, the axial angle between the z-axis and the state. And the phi over here represents the azimuthal angle of the state's vector on the sphere. So basically, the idea is to represent the state as a point on this Bloch sphere, and the Bloch sphere's radius is obviously 1 because it's normalized right here. So this gives us a convenient way of representing states visually, basically. So here are a few examples of common states represented on the Bloch sphere. So the first, the zero state of the z basis would be, of course, just along the z-axis, since theta is 0 and phi is also 0 for z for this state, if you could plug these in there. Of course, so moving on, for single qubit gates, here are a list of the most common single qubit gates. So as I mentioned earlier, we have the Pauli X, Y, and Z gates over here. And of course, these are due to the Pauli X and Y Z matrices in quantum mechanics, representing the spins of a spin half system. So the representation, these are the matrices, of course. And if we apply them to the computational bases, what do we get? We get we get 1, 1, 0. And this is 0, 1, which is, of course, 1. We also get the opposite and vice versa for this case. So X basically flips the canonical basis state to the other. And Y0, of course, do we get 0Y here, which is basically I0. Physically, this is equivalent to just 0. And of course, for here, we get I because I1 minus I. Oh, sorry, I appear to me made a mistake over here. And of course, you can multiply the, if you do this as well. So, uh, okay, we get this. And notice how these flip between these two basis states, basically. So the Z flips the plus state to the minus and vice versa. So this is called the phase flip operator. And for the Hadamard basis, as I mentioned earlier, we get plus and minus of these states. So the Hadamard gate over here is used for switching between these two basis states, which is quite useful actually for generating entanglement since the plus state, well, superpositions between these two states. And in conjunction with what's called the C-naught gate later on, we'll see that the Hadamard is useful for generating entanglement between basis states. So the S gate, or the phase gate, I believe, is another gate over here, which by itself seems to be quite arbitrary, but it is in fact the square root of the Z gate over here. So representing it as this may be more helpful, in fact. So I'm not gonna do these. I'll leave them up to you to explore. But basically the S gate is also just it is the square root of the Z gate. And we also have what's called the T gate, which is the square root of the S gate. So basically we have this relation over here. Now, what's special about the T gate is that the T gate is required for what's called magic. Magic. So it turns out that if we have quantum circuits without the T gate, which instead with just the Hadamard gate and the phase gate or the S gate and the C naught gate, gates which are only generated from this set is what's called the Clifford gate set, which we'll cover later. But this Clifford gate set can be simulated efficiently, but with a classical computer, which basically defeats the purpose of using quantum computers. But if we add the T gate, which is required for what's called a universal gate set, basically if we have an H gate, an S gate, C naught, which we'll cover later, and T gate, they they comprise of every gate. And this cannot be simulated efficiently. So moving on to the other gates, we have what are called X, Y, Z rotation gates, which are basically generalized versions of the X, Y, and Z gates. What these do, basically, they rotate our state along an axis, so along the X, Y, and Z axes, about a certain angle. So for this case, the RX gate, it rotates our state by like counterclockwise around the x-axis of the Bloch sphere by an angle theta. And this can be seen in the formula over here. This is obviously a rotational matrix. And for the y is it's the same thing basically. And for the z, it's the same thing over here. So let's move on from single qubit systems to multi-qubit systems. So how do we represent multi-qubit systems from single qubits? We do what's called the tensor product, which is basically the representation of two systems multiple systems at once. So a tensor product is an operation that combines two different systems. It helps us keep track of two different systems. So it's helpful to think of the tensor product of a relabeling operator in which we it adds in additional indices that keep track of multiple states of multiple systems and incorporates them into one system. So that was a bit of a mouthful. So let's look at an actual example. So let's say we have two vectors, A, B, and C, D. The way we perform a tensor product is that we multiply A by the first. We basically input this vector into the placeholder of A and multiply the vector by A, like so. And we do the same for B, and this is the result. Now, this may look a little bit cryptic, but let's look at a few examples. So let's say we have two systems, two qubits, basically A and B, and they are both in the zero state. What would this correspond to in our AB composite state? Well, if we perform the tensor product operation I just showed earlier, we get this form, which roughly translates into 1, 0, 0, 0. And then if we repeat this for different combinations, we start to see a pattern. It starts cycling from 1, and then it starts cycling to 1 in the second place, the third place, and the fourth place. So it's basically relabeling our system such that it's keeping track of these different combinations, which corresponds to the basis of composite system AB. Okay, so the next topic is what's called an operator of our composite system. So we do the same thing as we did with states, except we take the tensor product of our two matrices. So it's basically the same principle. We simply input this matrix into each different placeholder of the matrix on the left, and we multiply it by its value and place it in the new, and then we input it in its new place to form a new matrix. So 0 correspond multiplied by, of course, this matrix is all 0, and this corresponds to this matrix. 1 multiplied by this matrix is 1, 0, 0, 1, the identity right here, and so on. And then this is our new matrix in the basis I just mentioned earlier of our composite system. So, of course, another way of thinking of the tensor product is that, no, another way of thinking of operators of composite systems is that they simply apply each operator that they're a tensor product of to the corresponding bases of the corresponding constituent systems. So basically, if we have a operator that's a tensor product of an operator in A and B, then this operator applies to this state in A, this operator in B applies to this state in B, and the final state is simply the tensor product of the results of the two operations. So that's one way of thinking of composite operators. So using this, we can define what's called multi-qubit gates. Or so for the two qubit case, we can define what's called the C-NOT gate, which I mentioned earlier, which stands for controlled NOT gate. And the controlled part refers to a conditional operation. Basically, the NOT gate is only performed when it meets a certain uh, condition. So in controlled gates, we have what's called a control qubit. So would be our system, basically qubit 1. And qubit 2 is the target qubit. So the target qubit is what we perform an operation on, basically. And the control qubit controls whether or not we actually perform the operation. So for the CNOT gate, we apply a NOT gate on the target qubit only if the control gate, no, if the control qubit is in the state 1, basically. So before, if we have a control of 0 and 0 and a target of 0, afterwards we have a control of 0 and target of 0. And we have the same thing. So for control 0 and 1, we have 0 and 1. Why? Because the control qubit is not in its control condition. But if the control qubit is in 1, we can see that we apply a NOT gate on the target qubit. So if we represent this as a matrix, we can represent it as this form. And as you can see, because of course, if we take the tensor product of these, we take the tensor product of these, and then we can use this representation to convert this into a matrix. Now, expanding upon this, we can create 3-qubit gates. So the Toffoli gate is basically a higher dimensional CNOT gate. This time we have 2 control qubits, and the target qubit, only has a NOT gate applied to it if the 2 control qubits are both in the state 1. And you can keep going on and on and on. Notice that the control qubits have a small black dot in their circuit representation. This basically represents the control condition of 1, basically. If it was not a black dot, but instead it was white, it was not filled in, then the control condition would actually be 0. So it would be flipped. So for example, if I have a white dot here and a black dot here, the control condition would actually be 0 and 1. So we can generalize this framework to define what's called a controlled U-gate, which is basically a U-gate that's applied only if the control qubit meets a certain criteria. So basically, in this case, we only apply this unitary U on these target qubits only if this control condition is met by the control qubits. So now that we've covered gates, what single qubit gates and double qubit gates, let's talk about quantum entanglement. So the quantum state of each particle group cannot be described independently of the state of others, including when the particles are separated by a large difference. This refers to the state of being quantum entanglement, basically spooky distance, spooky action at a distance. Basically, we have 2 states which are seemingly interconnected. So if one state was in, for example, for this state, if one state is in 0, it's almost guaranteed that the other state is also in 0, and vice versa. And as you can see here, we use CNOT gates and Hadamard gates in order to generate these highly entangled states. And if you follow the algebra, which is not too difficult, you can see that is the case. Now, since this is a bit complicated, let me just draw the circuit diagram for you, which is much easier to remember. So first, we apply the Hadamard gate. And let's say this is 0, and this is A, this is B. And then we apply the CNOT gate conditioned on here. So this is what's called a Bell pair, which basically refers to the physicist behind Bell's inequality, which basically is false if quantum entanglement has occurred. So Bell was this physicist who designed an inequality which is supposed to be satisfied if the quantum theory of entanglement is false. And it was shown through experiment that this inequality is actually violated. And in the experiments, these tangled states are generated. So in his honor, we call them Bell pairs. And there are many other different Bell pairs. So there are different combinations of these. But they basically are same versions of each other, except they just have different relations. So if there could be another Bell pair, which is instead one. So this is one, this is zero, and this is zero, this is one. But the essence is basically the same. So moving on, we have what's called quantum. We can define what's called quantum circuits using our gates. So a quantum circuit is the quantum analogy to classical circuits, which is a model of quantum computation in which the computation is a sequence of gates, measurements, and initializations of the qubits. So we're viewing our operations on these qubits as information processing, basically. So if you recall from lecture, I believe, with lecture two, the evolution of a closed quantum system is described by a unitary operator. And according to lecture two, we saw that unitary operators are always reversible. Now, what does this implies that quantum gates themselves are always reversible, which is in contrast to classical gates. So as you can see in the AND gate right here, we have two inputs and we get one output here. And this obviously isn't reversible. You cannot tell what the inputs were just starting from the output, except maybe the input here. But if we had got a zero here, we would have three different options. So basically, it isn't reverse. They are irreversible gates in the classical case. But for the quantum analogy, for the quantum case, take for example the C naught case. The C naught matrix is a unitary, so from each of these entries, we can always tell what the input is. So I think I drew a version of this earlier on, but how do so basically let's go over how we visualize quantum circuits. So I actually spoiled this. I drew a short representation of a quantum circuit over here. But basically, we represent quantum circuits through first we have wires, which basically represent the flow of time, basically the order of processing. And before these wires, we represent qubit labels, which basically represent which operations are applied to which system. So there are many different conventions that you could use for the ordering of these, but the convention I like to use is that the top corresponds to the most left, right here, like so. But this notation varies. So when reading papers in quantum information theory that have diagrams of circuits, it's good practice to just take note of what notation they're using for the order of the labels. So next we have what's called layers, which basically represent quantum operations, quantum gates, measurements, initializations that occur at the same time. So for example, here we have these two Hadamard gates, and these two Hadamard gates would be applied at the same time on qubits Q0 and Q3. And then afterwards, this layer would be executed, and we had these C naught gates applied here, and so on and so on. So finally, next over here, we have what's called a measurement. So measurements are usually represented by these little gauge diagrams. And these represent a measurement such that a quantum state collapses and we end up with classical information. Now, most of the time these measurements are at the end of the circuit after we've done all our processing. But sometimes they can be in the middle of a circuit. So we measure, we collapse our state, and then there's usually another initialization of the state afterwards, and then we keep going on and on. That's what's called a mid-circuit measurement, which is an active field of research in quantum information theory today. So, of course, this is another example of a quantum circuit, which I mentioned earlier, which is the Bell pair generator, which I mentioned earlier. And then this is another example of a quantum circuit that contains basically subroutines in here. So these are gate representations of different routines over here. And this is the HHL algorithm, which basically solves systems of linear equations using quantum computing efficiently. Okay, so this next section is just a short side note on the exponential Pauli matrices. You can skip this part of the video, but it's just basically useful tips and tricks when dealing with the math for computing gates. So basically, as I mentioned earlier, we have these rotation gates uh, around the XYZ axis. But in general, we can also have rotations around an arbitrary axis on the Bloch sphere. So we go down here. So let's say we have uh, this vector, a three-dimensional unit vector, which represents our rotation vector. Theta, rotation angle, which is a real number. Then if we have this exponential, we get this result over here, which is our rotation. So how do we prove this? Well, notice that, okay, where we have the dot product of the vector and the Pauli vector, which is basically just a vector representation where each entry are the Pauli matrices over here, and this is just a bookkeeping notation, just to have a short form for this sum. So we prove this, we actually exploit the fact that these are Hermitian, of course, and every Hermitian operator, of course, has the spectral decomposition, which is represented as follows over here. And these are the eigenvectors of our Hermitian matrix, and this is the eigenvalue. So since A is a Hermitian matrix, if we take the nth power, we end up with this representation over here. And as I mentioned earlier, from the definition of the exponential of matrices, we can go ahead and represent this as the infinite sum of such exponentials. And this reduces, of course, to over here. Because of the spectral representation, we end up with this representation over here. And this simply reduces to the exponential of ei to theta lambda k. And then since we can represent this vector sum as this matrix, if we can show this is Hermitian, then we are basically done. Well, we're basically done. Since it is Hermitian, if we calculate the eigenvalues here is 1 and -1, And so this basically reduces into this representation. And then if we go into the algebra over here, we can see that it reduces to this form over here. So this is basically the generalized version of these Rx, Ry, and Rz representations. And we can actually use this formula to derive these matrices. Okay, that's all for today. I'll see you in the next lecture.